Professor Huckabee here. This is another lecture that was given last spring, and it's on Chapter 3, Acids and Bases. If you have any questions, you know where to reach me at my email. And without further ado, here is your to-do list. You have the homework 4 assignment, it's due Friday, as well as working as many Chapter 1 through 3 problems as you can, because hopefully you have already done Chapter 3 a bunch of the Chapter 3 problems and done the Chapter 3 reading. Please don't forget that the first exam is on September 15th, and go ahead and start trying to work the old exam and practice exam problems. Good luck.
Besides a silly meme, why do we serve lemon with fish? Does anybody know? Have an inkling maybe? Small hint. It begins with trimethylamine oxide. Now, we're all in a second-year chemistry class, so I can't really expect anybody to know this since I also had to Google it earlier today. Apparently, fish use this molecule as a way to keep too much salt from entering their bodies, especially if they're in a saltwater environment, and especially if it's cold salt water. And something that's a little strange is whenever a fish dies, enzymes in their cells convert this molecule to something that smells really bad, trimethylamine. This is the classic fishy smell. And so, if you have a nice fish and chips plate up there, what you'll do is you'll sprinkle some citric acid from lemons onto it, and you will move that trimethylamine from a volatile organic compound to something that now has a positive charge and is not volatile anymore, which means you cannot smell it. So you turn a pretty smelly fish into something much tastier just using organic chemistry. All right, so where do we leave off? We left off, we just kind of like mentioned REO and all the things that you use to compare conjugate bases, right? REO being atom, resonance, induction, orbital. And if you remember, we kind of hit these slides at the very end. I'd like to go back and just touch on them again. That way we all have it in our minds. I'm now realizing I didn't post the slides from last time. So as soon as tomorrow morning, I hope I'll post all the slides so you'll have them. All right, so atom, as a rule, essentially means more electronegative atoms like having charge. So atoms with those charges will be more stable than less electronegative atoms, right? So a carbon cannot hold a negative charge as well as a nitrogen. So any conjugate base involving carbon will be less stable than a conjugate base involving nitrogen. Same goes for oxygen. Now, as you move down the table, no matter where you are, those atoms are able to hold a charge better. And that's because if you imagine, I'm going to just draw some small circles here. These are our pretend atoms. Okay, so as we go down the table, let's do this. As we go down the table, the atoms get bigger because they have larger nuclei and because they have larger electron clouds overall. You can imagine that if you have these these circles of different sizes, that if you kind of just insert a negative charge inside this small cloud, that it's going to have a large effect because the cloud already itself was pretty small, right? But as you increase the size of the overall electron cloud and you add a negative charge, it has less effect because in the very large atoms, they probably already have more than 30 electrons by themselves. And that makes a big difference when you compare, say for instance, we'll do selenium and oxygen. Remember, oxygen has 8 total electrons before you put the negative charge in, and selenium has a lot more, like at least 30, I think, off the top of my head. I forget the number. But you can imagine how that makes a much less impact And so for that reason, the selenium would be able to hold the negative charge a lot better, and the conjugate base would be more stable. And if you have a more stable conjugate base, you have a stronger acid. Hopefully you're completing that sentence in your mind now, and I don't have to keep saying it over and over for it to sink in. All right. Resonance. Do you all remember resonance? It's the principle of delocalizing a negative charge over many atoms, and if you do that, then the overall negative charge is felt less by every individual atom, and the molecule, the conjugate base is more stable. Okay, so this happens for this carbon-based carboxylic acid, but it also works for amines. I'm just showing these as two random examples, and I just picked out some random numbers and structures from the Evans pKa table. And these just go to show you that as you increase the amount of resonance from none to now one carbonyl, to a carbonyl and some more pi electron stuff, to very involved structures, you get more and more acidic because you're able to move that negative charge onto different atoms. Okay, 2 carbonyls and a phenyl ring versus just 2 carbonyls by themselves. One thing we didn't talk about last time is amine basicity. And I'm going to actually touch on it now because, you know, I didn't do it last time because we went through it kind of quickly, but it's something that you need to know because amines are a special, kind of a special circumstance in organic chemistry because often we aren't talking about them as acids, we're talking about them as bases. And you can use a very similar set of logic rules to think about amine basicity as you would regular acidity of protons. Okay, it's a little easier with amines actually because they're already so basic. So if you notice, in these 4 structures, they all look a little different, but hopefully you notice that the one on the left, that p electron, I cannot say what I want to say. The lone pair is in a p orbital that is localized completely on the amine, right? Hopefully you see that in that cyclohexylamine atom. When you have, or molecule, when you have cyclohexylamine with 2 hydrogens, it has a lone pair that is completely localized onto the nitrogen atom. All right? However, we all know from several of the homeworks and several of the other problems that you've worked in your book and here with me that nitrogen p orbital lone pairs like to delocalize, don't they? And it turns out that essentially this type of molecule is the strongest an amine can be in terms of basicity because that lone pair in the p orbital really likes to act as a base. If you do anything to delocalize that lone pair, you're going to be reducing the basic strength of the amine because the electrons, instead of just being available to do acid-base chemistry, they want to be delocalized throughout more atoms. So, for instance, if you look at the 3rd structure there, it's called aniline. Hopefully you recognize a resonance pattern here, kind of like an allylic anion, right? With the double bond and a lone pair next to it, where you can move the lone pair throughout the benzene ring. And make several structures, each that are delocalizing that lone pair throughout the molecule. And so if the lone pair is delocalized, it doesn't act as a base nearly as well because the charge is all spread out. And that's primarily the reason why here the pKa of the nitrogen is much higher the pKa of the cyclohexylamine nitrogen is much higher than that of the aniline nitrogen. Because do you remember what pKa means? pKa means that if you have here, let's say the pKa of aniline, 10.7, that means as you go higher in number, so we'll say this is like 30 and this is 0, okay? As you go higher in number, the amine will be deprotonated, right? So the structure you're looking at will look like that, where you have a negative charge. Negative charges are in blue today, in case you were wondering. You'll have a negative charge on the nitrogen, and this will serve as a very good base. Okay? If you go below that, however, that's when this has acted as a base, and now you have an extra acid, or an extra proton there. So essentially, in basicity, the pKa, instead of a measure of the acidity, now you think of as a measure of basicity with amines. Okay, it's kind of like it's backwards a little bit. So what that tells you now is that cyclohexylamine is more basic than is, let's again go to the aniline. We'll put it here. It's 0, 30 again, because now because now at a lower pH, that's when you are only able to generate that acid form. So that means if you were trying to deprotonate something, if you're trying to deprotonate a chemical in this range between, 4.6 and 10.7, you could not use aniline, because you would not have aniline in the acid form. You would have to use the cyclohexylamine if you wanted to do that reaction. Does that make a little sense? Of these two, perhaps? Yeah, I know, it's a little confusing. It's like the exact opposite of what we were talking about before with acidity and conjugate bases, but amines are weird. So in the same way that you just kind of have to absorb the knowledge of conjugate bases and the stability there, you need to try and absorb the basicity lessons about amines too. One really weird thing is when you consider the basicity difference between pyridine and pyrrole. I don't know if you can actually pick out in these four structures which is pyridine and which is pyrrole, because they're old names that we have in chemistry since like the beginning of organic chemistry. But pyridine is the one with the 6-membered ring with that structure, and pyrrole is the 5-membered ring with this structure. And they both have lone pairs, and they both have conjugated rings. But both are super different because one of them has a lone pair that is completely localized on the nitrogen, and one of them has a lone pair that is completely delocalized on the nitrogen. Do you remember from your homework which one of these might be the case? The delocalized one is pyrrole, because remember in your homework, the pyridine had a lone pair that was completely sp2, right? We checked the hybridization of a pyridine in a nicotine molecule, and it was completely sp2 because it's totally localized. And that really plays a big part into why one is much more basic than the other. And you know that one is much more basic than the other because the pKa of pyridine is 5.2, which means from 0 to 5.2, pyridine is still going to be in its acid form. Whereas pyrrole won't be in the acid form until it hits 0. Do you see that? Take a second and try and make sure that you're really absorbing this bit of concept here. At 0 is when pyrrole is protonated. Below, it's in its acid form. Above 0, pyrrole has not acted as a base. However, at 5.2, pyridine acts, or below 5.2, pyridine acts as a base. Which means, in this opposite day world, pyridine is actually the strongest base, right? Because from 0 to 5.2, it has done the reaction you wanted. All right. So moving on in our REO recap, we have induction. And remember, induction works because of the formation of dipoles next to a conjugate base. And the example we have here is one with carboxylic acids. We'll just keep this as a CH3 for now. Okay, so what's the first thing you do when you're talking about conjugate base stability? You have to make the conjugate base, right? Because this is the acid. Whoops. This is the acid up here. There's still a proton on it. So let's draw the conjugate base of this molecule. There we are. Nice, shiny conjugate base. Okay. Now, does anybody know why that molecule is special? Does it have any special atoms? Does it have resonance? Oh, I saw some people's eyes spark up when they heard resonance. Yeah, that's because you guys love organic chemistry, right? Resonance just gives you joy. This has resonance. And what that means is, as you already know, because you're experts, you can move the electrons onto the different oxygen if you want, because they are in conjugation. Awesome. Oh no, the negative charge is in black instead of blue. That's horrible. There we go. Now the world is happy. Okay. So we have a resonance that lets us spread out that negative charge across the 3 atoms. Do you see that? Oxygen, carbon, oxygen. And the reason why induction works is because just like 2 magnets that are happy to come together, north-south, you generate a dipole if you have something on the carbon, whoops, where there's a partial positive on the carbon and a partial negative outside. Okay, so just the nature of having that partial positive charge near where you've generated a negative charge automatically stabilizes the conjugate base. And because you stabilize the conjugate base, what does that mean about the acid? Oh, I heard some murmurs. Good. I'm going to assume those murmurs meant stronger acid. Good. So up here are just a few examples of parts of the molecule that could make a dipole. So as you increase the number of electronegative atoms on the carbon, the dipole increases and you get better stabilization and the pKa drops. Now, by show of hands, who feels like maybe the pKa, or sorry, that acidity and pKa still aren't super linked in your mind? You know, like if you see a pKa number, okay, that's good. It's hard to really understand how acidic that is. And that's good. I'm glad that I saw some hands because, you know, it takes a long time to like get it sometimes. It took me much longer than I like to admit to really have this cemented in my mind. And so I like to do something to help me pictorially see what it is that pKa and pH, how they're linked together. And the way I like to do it is to, instead of imagining a horizontal line like I've been drawing, kind of imagine a vertical line. And your pKa that you're talking about falls somewhere in the middle. And remember, pH increases in acidity as you go down, right? So I'm going to just draw 0 down here. And I'm going to draw 14 up here. And I'm going to keep the colors red and blue just like litmus paper. Because litmus paper turns blue when you have a base and red when you have an acid. If you ever go below the pKa, nearer to 0, that's when it's stronger. That's when the environment is a strong acid, right? When it's nearer to 0. So if the environment nearer to 0, below the pKa, is a stronger acid, that means your molecule is going to have an extra proton. It's going to be protonated, acidified. If you go above the pKa, you're closer to 14, just in this general example. You know, maybe your pKa is already higher than 14, but just as a way to think about it. You go above the pKa, and you're going to be in a more basic environment. So bases love to take protons, and your molecule above the pKa will have a less proton because it will be deprotonated. I don't know if that will help, but maybe it'll be just another way that it will hopefully stick in your mind somehow. Because it's really good if you can just pick out numbers and say, oh man, 4.76, higher pKa than 0.65. So that means 4.76, that molecule is less acidic than 0.65. Just as a frame of reference, the example that we were using before, hydrochloric acid, its pKa is like -9. So it's super, super acidic. pKa is very low. And sodium hydroxide, OH minus, the pKa of this guy is like 30 something. Very high. So hopefully we explain it in so many different ways that something will stick. All right. So then what about the last thing, orbital? Does anybody remember what orbital stands for? That's a stupid question, right? It stands for orbital. Yeah. No, this basically just tells you that as you go down the amount of p contributions in your hybrid orbital from sp3 to sp2 to sp, that's when things start to get more acidic because the negative charge is physically closer to the nucleus. All right. So that was our REO recap. Hopefully doing this twice helped everybody. Now we get to the good stuff. Now we get to how does REO actually help us in comparing things? Because, yeah, sure, it's easy to compare something like ethanol versus mercaptoethanol. I mean, what's the difference there, right? We already know REO, atom, the mercaptoethanol makes the more stable conjugate base, and so it's more acidic. But what if I were to draw you something like propylene versus dimethylamine? Do you feel super confident that you could know those? Because now you have this double bonded molecule versus some random amine. Without looking at the pKa table, can you say which one is more acidic than the other? Okay, I'm seeing some nods. Good. Looks like you guys are doing some homework maybe. Essentially, you go through REO each time and you say, okay, A, R, I, O. A, the hydrogen is on a carbon for one and a nitrogen for the other. That means the second is preferred. Resonance, the first will be preferred, right? Because it's on a double bond. Or would it? Does everybody see that the conjugate base of this molecule does not actually have resonance stabilization? Yeah? If you doubt me, which is cool, answer me this. Where or what is the hybridization of that lone pair? Whoops, it's covered up. Is it a p orbital or an sp2 orbital? All right, I heard some sp2s. Maybe if I draw it like this, with the carbon here, and I draw the hydrogen kind of like coming out, and the lone pair coming out the other way, this way, and the p orbital sitting on top. Does that help you see that that lone pair is actually in sp2? And so does not actually have resonance with the double bond as we see it here? They aren't physically next to each other or overlapping enough in just this configuration to give you good resonance as it stands here. All right, so all that to say, they don't have resonance. Induction, there isn't really anything to write home about because here you don't really generate any extra dipole that would help you. Same for here. And then the orbital, sp2 versus sp3. Right? Do you all see that the hydrogen on the nitrogen is at sp3? Hopefully you do. And the first is preferred. But because A is higher in the food chain, A gets the more stable conjugate acid. And that's always going to be the case where we're looking at A is greater than R, greater than I, greater than O. And that's why we specifically say ARIO. Because if you follow that step by step for whatever comparison, you will get to the right answer for what is the most stable conjugate base. And just to make sure that this is beaten to the ground enough, let's come back to our good friend, mercaptoethanol, and we'll compare that to difluoroethanol. Please, somebody stop me right now if when I tell you that doing ARIO, ooh, the lights came off again. It's really a shame that they do that every time. Okay, back to doing. There we go. All right, so hopefully no one feels like they're lost if I say that the first is preferred because it's S in the atom here, and that beats the induction of the two F's that are had here. Hopefully everybody sees that atom wins that one as well. No? Okay. So because in ARIO, every time we make an assessment, we go through the list, ARIO. Neither of them have resonance, and the orbital is the same for both because they're both in sp2 3 orbitals, right? sp2 3 orbitals on that hydrogen. So when we make the conjugate base of each, oh, it's a bad S. There we go. Oh, I did it again. Look at that. Negatives are blue today. There we are. And we have the two fluorines here. There is a dipole associated with both of these fluorines, right? A big one, since it's two fluorines. However, in the ARIO framework, each letter means a lot more than the next letter. So even though I is a big difference in favor of the difluoroethanol, because A was still a big difference for the mercaptoethanol, we have to go with the first one as being the most stable conjugate base. Every time. So it might even help you to draw it vertically like this. That way you can rank it in your mind intrinsically that A is best, then R, then I, then O. If that's how you have to do it, that's fine. But you need to get that stuck in there that this is the priority that is given to each of them. All right, so let's do one more just to be sure that we're all on the same page. Okay, what about this example? Let's say that we have butadiene versus butyne. And we're going to be looking at this proton on each. All right, so we make our conjugate bases. Minuses are blue. And then we go through our A, R, I, O. All right, so atom. Are there any differences in atom? No, right? They're both carbons. So it's the same. Boom. What about resonance? Are there any differences in resonance? What if I told you there were? What if I told you that now there are differences in resonance because you have a conjugated system? And so now, without touching this negative charge, you could move the resonance, or you could move pi electrons around, just like we're allowed to do in any circumstance, and make that type of molecule. Is that a particularly happy molecule? Probably not. However, did you just move a negative charge around? You did. So we'll call that a half a point for the first one, because it's not a great structure, but it is still technically valid. Induction. Are there any induction concerns here? Good. I'm seeing some shaking of the head. That's great. All right. Last, orbital. Is there an orbital? Yeah, I'm seeing some nodding. Good, because you all know that the second one is, or the first one is sp2, and the second one is sp, right? So that means that the second one gets, we'll call it 1 full point, whatever that means. But because ARIO has everything prioritized such that even a half a point for resonance means so much more than a full point for O, you could say that the conjugate base of the butadiene is more stable than for butyne. Is that right? Do you believe that?